Yeah, so I had to interrupt recording because I forgot to put the audio input from my MacBook microphone, and that basically messed up a little bit. So this the video has to be two parts because unfortunately I just don't have enough time to edit this together. All right, so we're at program counter. I'll just double check this one. Yeah, program counter is the same as the PC register in other instruction set architecture. Here it acts as a separate entity, but the task of the program counter is the same, pointing towards the next instruction to be executed. Program counter and pointing towards next instruction to be executed. All right, perfect. So data memory. I read this dynamic memory, but it's data memory. The memory in a Y86 is normally referred to as data memory DMEM. The memory is conceptually a large area of bytes holding both program and data. Excuse me. Y86 64 programs reference memory locations using virtual addresses. A combination of hardware and operating system software translates these into the actual or physical addresses, indicating where the values are actually stored in. All right, so you can see, and you're saying point this to 1,000. You can have multiple programs running that has the virtual memory of 1,000, but their actual underlying memory is probably different. That's what it is. Y86 64 programs. Reference memory location. Using virtual addresses. Yep. And a combination of hardware and operating system software translates those. Actual memory. All right, so now we go to program status. A final part of the program state is the status code stat, indicating the overall state of program execution and other status bits. It will indicate either normal operation or that sort of exception has occurred, such as when an instruction attempted to read from an invalid memory address. All right, so we can move to Y86 instructions. The instruction set of the Y86 instruction set architecture is very limited and is a subset of the instruction set of IA32. I feel like we had IA32 in UBC as well. And instruction in the Y86 instruction set architecture looks like the following. So mnemonic source destination. Okay, so movement instructions. Following is the instruction set of Y86. So you can see movement. So we have register to register. And then I need to write these. Immediate to register movement. I R move Q. Immediate. Movement. Memory to register movement. Memory to register immediate. Okay. Makes sense. Register to memory movement. Conditional movement. Oh, interesting. C move Q. All right, and I'm not gonna write down the arithmetic, but basically add cube. It adds R8 to R9, stores everything to R9. Sub Q. Subtract R9 from R8. Right, I actually have access to these. Go here, go to this. Alright, so sub Q. Oh, immediate move to immediate R move K. Move 1 to R. Let's use R8. For 1 cycle. Move K. Put 3 in R. R9. Now we do sub Q. R. Oh, we need the. Let me just make this bigger. R8. R9. Okay, it's 3. Something's wrong. Invalid arguments? Oh shit. So I literally do this, no? Cycle. Oh. What's wrong? Redo is Command Shift Z. Oh, you see, I had an ampersand. Alright, fair enough. But yeah, it puts it in R9, so it puts it in the right hand side. Alright, same thing for AND. Same thing probably for XOR. So these are the jumps. I should write the jumps. Just gonna mute this for a sec. All right, so now we have the jump instructions. We have the JMP unconditional jump, JE jump if equals jump not equal, jump not equal, jump if greater, jump if greater or equal. JL stack instructions is adding an element to the top of a stack, and okay, so stack instructions are pop and push. There are some details that I forgot, but basically your push basically needs to offset a certain amount. The pop needs to also calculate that. And then we move to subroutine instructions. Then we have call and read. Then miscellaneous instructions. I write it down as MISC. So knob is don't do anything. And halt is stop executing. Instructions. So hardware, so logic, okay, now we move to logic design and hardware control language. Logic design. In hardware design, electronic circuits are used to compute functions on bits and to store bits in different kinds of memory elements. Most contemporary circuit technology represents different bit values as high or low voltages on signal wires. In current technology, logic value 1 is represented by a high voltage by around 1 volt, while logic value 0 is represented by a low voltage of around 0.0 volts. By assembling number of logic gates into a network, we can construct computational blocks known as combinational circuits. Alright, so by assembling a number of logic gates into a network, we can construct computational blocks known as combinational circuits. Hardware control language. On the other hand, hardware level language or hardware description language is the language that we use to describe the control logic of the different processor designs. Data types in HCL. There are two data types in HCL which are mentioned below. There are booleans and there are integers. And statements are, a statement in HCL looks like somehow like this. So bool A equals a bool expression, int A equals an int expression. HCL operations. The operators in HCL are divided into two categories: logic operations, AND operator, or operator not operator. And I actually keep forgetting how to do XOR. The combination of OR and so if XOR, if you have two similar together, do that. So basically you have to negate one to have the zero of it. Oh, maybe, yeah. So maybe because we both want zeros and ones, you basically say what? You basically say the negatives and then you OR it. Okay. The negated, not negatives, the negated PQ, you AND those, and then you have PQ, you AND those, and then you OR it probably. And then you have, okay, not operator that work comparisons a equals b, a not equal b, a less than b, a less than or equal b, a greater than equal b, a greater than b. And simple example of logic design with their HCL statements. So a equals b or and not. Bit equality example of logic design and its HCL statement. Below is a logical circuit that will return 1 when both inputs are same. And will return 0 when both inputs are different. This circuit is Boolean combinatorial logic as it deals with 1 bit. HCL for above logic design. So you have Boolean. This is whatever equals to. This is XOR. Oh, I was actually right. Okay. Because yeah, you do A and B, and then you OR together the negative version of that. Negative A and negative B. That not just negative version of that. Sequential Y86 implementation. A processor where sequential Y86 implementation is implemented is known as SEQ or SEC. Y86 implementation is implemented is known as that. Sequential implementation refers to the sequential execution of instructions, non-pipelining. Conventionally, the Y86 has sequential implementation, but we can also extend its capabilities to pipelining too. Stages of SEC. Following are the stages of Y86 sequential implementation. Let me write this. So you have instruction fetch. In this stage, the processor fetches the next instruction from memory by getting the address from the program counter and PC is updated. Stage. Fetches the next instruction from memory by getting the address from the program counter. And PC is updated. And then instruction decode. In this stage, the fetched instruction is decoded. Instruction. Excuse me. I mean, thanks, but nobody watches these, but like actually watch these, but they have a lot of problems. All right. While CISC instructions varied in length, RISC instructions are all the same length and can be fetched in a single operation ideally. Each of the stages in a RISC processor pipeline should take one clock per cycle so that the processor finishes an instruction each clock cycle and average one clock cycle per instruction. Pipeline problems. In practice, however, RISC processors operate at more than one cycle per instruction. The processors might occasionally stall as a result of data dependencies and branching instructions. A data dependency occurs when an instruction depends on the result of a previous instruction. A particular instruction might need data in a register which has not yet been stored, since that is the job of a preceding instruction which has not yet reached that step in the pipeline. For example, add more instructions that are independent of the first two. In this example, the first instruction tells the processor to add the contents of register R1 and R2 and store the value in register R3. The second instructs it to add R3 and R4 and stores the num in R5. Okay, so maybe this is different. Yeah, it's different. Okay. We place this set of instructions in a pipeline when the second instruction is when the second instruction is in the second stage. The processor will be attempting to read R3 and R4 from the registers. Remember though, the first instruction is just one step ahead of the second one, so the contents of R1 and R2 are being added, but the result has not yet been written into register. Register 3. The second instruction therefore cannot read from the register 3 because it hasn't been written yet and must wait until the data it needs is stored. Consequently, the pipeline is stalled and a number of empty instructions known as bubble go into the pipeline. Data dependency affects long pipelines more than short ones, since it takes a longer period of time for an instruction to reach the final register writing stage of a long pipeline. MIPS's solution to this problem is code reordering. If, as in the example above, the following instructions have nothing to do with the first two, the code could be rearranged so that those instructions are executed in between the two dependent instructions and get the pipeline and be arranged so that these instructions are executing between the two independent instructions and the pipeline could flow efficiently. The task of code reordering is generally left to the compiler, which recognizes data dependencies and attempts to minimize performance stalls. Branch instructions are those that tell the processor to make a decision about what the next instruction to be executed should be based on the results of another instruction. Branch instructions can be troublesome in a pipeline if a branch is conditional on the results of an instruction which has not yet finished its path through the pipeline. For example, loop add R2 and R1, put it there, sub R4 from R5 probably, or R5 from R4. I'm not sure because we store things here, so it really depends which one comes first. The example above instructs the processor to add R1 and put it there, then subtract R. Okay, so it is the other way. Storing the difference in R6. In the instruction, B equal stands for branch if equal. If the contents of R3 and R6 are equal, the processor should execute the instruction labeled loop. Otherwise, it should continue to the next instruction. In this example, the processor cannot make a decision about which branch to take because neither the value of R3 or R6 have been written into the registers yet. The processor could stall, but a more sophisticated method of dealing with branch instructions is branch prediction. And this is the part, can I make this about which branch to take because we are pipelining stuff, we don't know the values of those two. So basically one is in instruction execute, hasn't come to being written. The other one is instruction decode, that's sub R6, and the other one is instruction fetch. Right, the processor could stall, but a more sophisticated method of dealing with branch instruction is branch prediction. The processor makes a guess about which path to take if the guess is wrong. Anything written into the registers must be clear, and the pipeline must be started again with the correct instruction. The processor makes a guess about which path to take. If the guess is wrong, anything written into the registers must be clear, and the pipeline must be started again with the correct instructions. Some methods of branch prediction depend on their typical behavior. Branches pointing backward are taken about 90% of the time, since backward pointing branches are often found at the bottom of loops. On the other hand, branches pointing forward are only taken approximately 50% of the time. Thus, it would be logical for processors to always follow the branch when it points backward, but not when it points forward. Other methods of branch predictions are less static. Processors that use dynamic prediction keep a history for each branch and uses it to predict future branches. These processes are correct in their history of each branch and uses it to predict future branches. These processes are correct in the predictions 90% of the time. Still, other processors forgo the entire branch prediction ordeal. The RISC system 6000 fetches and starts decoding instructions from both sides of the branch. When it determines which branch should be followed, it sends the current instruction down the pipeline to be executed. In order to make processors even faster, various methods of optimizing pipelines have been devised. Super pipelining refers to dividing the pipeline into the more steps. The more pipeline stages there are, the faster the pipeline is because each stage is then shorter. Ideally, a pipeline with 5 stages should be 5 times faster than a non-pipeline processor, or rather a pipeline with 1 stage. The instructions are executed at the speed at which each stage is completed, and Um, um, all right, let's read from up there. Super pipelining refers to dividing the pipeline into more steps. The more pipe stages there are, the faster the pipeline is because each stage is then shorter. Ideally, a pipeline with 5 stages should be 5 times faster than a non-pipeline processor. Or rather, a pipeline with 1 stage, the instructions are executed at the speed at which each stage is completed, and each stage takes 1/5 of the amount of time that the non-pipeline instruction takes. Thus, a processor with an 8-step pipeline, the MIPS R400, will be even faster than its 5-step counterpart. The MIPS R4000 chops its pipeline into more pieces by dividing some steps into 2. Instruction fetching, for example, is now done in 2 stages rather than 1. The stages are shown here: instruction fetch, register fetch, instruction execute, data cache access first half, data cache access second half, tag check, write back. Superscalar pipelining involves multiple pipelines in parallel. Internal components of the processor are replicated so it can launch multiple instructions in some or all of its pipeline stages. The RISC System 6000 has a forked pipeline with different paths for floating point and integer instructions. If there is a mixture of both types in a program, the processor can keep both forks running simultaneously. Both types of instructions share 2 initial stages: instruction fetch and instruction dispatch. Before they fork, often, however, superscalar pipelining refers to multiple copies of all pipeline stages. In terms of laundry, this would mean 4 washers, 4 dryers, and 4 people who fold clothes. Many of today's machines attempt to find 2 to 6 instructions they can execute in every pipeline stage. If some of the instructions are dependent, however, only the first instruction or instructions are issued. Dynamic pipelines have the capability to schedule around stalls. A dynamic pipeline is divided into 3 units: the instruction fetch and decode unit, 5 to 10 execute or functional units, and a commit unit. Each execute unit has reservation stations which act as buffers and hold the operands and operations. Instruction fetch and decode units, so we have reservation stages, 4 of them, and then we have integer, floating point, load, and store. And then in order commit, what is this? There is a commit. What is there? I saw the floating point. All right. We can move on for now. While the functional units have the freedom to execute out of order, the instruction fetch and decode, fetch/decode, and commit units must operate in order to maintain simple pipeline behavior. When the instruction is executed and the result is calculated, the commit unit decides when it is safe to store the result. If a stall occurs, the processor can schedule other instructions to be executed until the stall is resolved. This, coupled with the efficiency of multiple units executing instructions simultaneously, makes a dynamic pipeline an attractive alternative. Alright, so I'm gonna refresh and I will come back with another video. Thanks for watching this one.